We're going to go over a example problem. This example problem has multiple parts. The cool thing about this example problem is that we can utilize all of the different models to solve this. Now, just so you know, the different kinds of practice that I give you, if you approach the same way that I'm about to approach it, there's no way you can get it wrong. It is a surefire way. So let's begin. So here we have an object with initial velocity of 10 meters per second. It's thrown upwards from a height of 2 meters. And I'm going to determine the following. How high will the ball go? How fast will the ball be when it lands? How fast is the ball going when it reaches back to a height of 2 meters? How fast will the ball be going when it reaches a height of 1 meter? Okay, so here's a lot of different things, 4 different things, and I just want to make one big distinction. I briefly touched upon this in the previous video, where we just went over the notes, where I said this looks a lot like the kinematics unit, with one huge caveat, right? And that caveat is that here, for the energy model, time isn't a variable. Now, so that is a big distinction. So I guess in the future, if you ever see that time is a variable, there's a high chance that you'll probably have to use kinematics maybe even alongside this energy model to help you out. Okay, so let's begin. The very first thing that you should always do, right, is you should always be sketching out these scenarios. So it looks like we are looking at how high it goes when it reaches back to a height of 2 meters, and when it reaches a height of 1 meter, and when it lands. So that's 4 different instances. So let's do it. We have a ball, and it starts off at a height of 2 meters. Okay, so right here we can say this is h of 2 meters, but the ball is moving upwards with a velocity of, what did I say, 10 meters per second. All right, so boom. This is scenario 1 right there. All right, scenario 2, we'll do this in chronological order, meaning so it first rises up to a max height. All right, so for here, we don't know what the max height is. That's what the problem is looking for. We do know that the velocity at max height, or the peak, is 0 meters per second. And that's that. Okay, so this is scenario 2. All right, scenario 3. Scenario 3, it goes up, right, and it comes back down to its original height of h is equal to 2 right there. And so what is the velocity? If you remember this from the kinematics unit, you probably already know the answer for that, but I want to show you how we can do this mathematically. And the very last one, all right, so we have a ball, gets shot up, and it's landing. All right, so here our height is 0, but we're looking for the final velocity. All right, so here we have our 4 different scenarios, and look at the previous video, what I want you to do is identify the types of energy that we start off with. Okay, so kinetic energy is velocity dependent, okay, and potential energy, or gravitational potential energy in this case, is height dependent. So I'm writing that there, and we're just going to let's create a little table just to speed things up. Oh man, that is not a straight line. Let's make it a straight line. There we go. All right. So in the beginning, it is moving, and we are above a height. Okay. Scenario 2. In scenario 2, we are above a height, but we are not moving at the peak. All right. Scenario 3. We are moving. We're moving downwards, and we are above a height. Scenario 4. We are moving, but we're about to hit the floor. So that is a big fat X. Okay. So we have this right there. And just to make sure conservation of energy is being followed, we're going to do a energy bar chart as well. Okay. Once again, all of these different models are there to help you out. Please don't skip them. LOL, right? So this is scenario 1. This is scenario 2. And as we go from scenario 2 to scenario 3, and as we go from scenario 3 to scenario 4. All right, so we have these different scenarios. Apparently, it's really, really funny. Get it? All right. Anyways, scenario 1 So we'll do U, K, and ME, or it's not ME, but total energy. Remember that total energy there is important because that total energy lets you know if anything is affecting the system. And quick little hint: until we get further into the unit, your total energy will always be the same as your final energy. But it's good to recognize that. All right. So based on our little chart there, we can say that we start off with some amount of kinetic energy. All right, I'm just going to do everything in black. Yes. All right, we start off with some amount of kinetic energy. Do we know how much? No. Okay, we start off with some amount of potential energy. Do we know how much? No. Right? This is just a conceptual graph, but we do know that it's double the size. So potential energy plus kinetic energy is equal to total energy. The middle part, we got to identify the system, right? So here, of course, it's the ball, and this is the Earth, right? And there's nothing, there's no air resistance, there's nothing, there's not a bird that gets in the way, right? There's nothing that interacts with the system, so we can say that our total energy initial is equal to the total energy final. Okay, this is a good check to have. All right. So in scenario 2, when we reach our max height, boom, boom, okay, our kinetic energy is 0, like we discussed up there, and so we only have potential energy. All right, next, when it goes from max height to back to its original height of 2 meters, right? Did anything interact with the ball? No, right? No one swatted the ball out of the air, right? There wasn't, I don't know, a little toddler that got in the way and you hit the toddler, right? None of that. So we can say, well, if it's back to the original height, right? So let's say we go from a height of 2 meters, then we go back to a height of 2 meters. And if we said that this right there was the amount of energy we had at 2 meters, we can say, well, that's the same amount of energy we had at 2 meters potential, and therefore this has to be kinetic. Now this is really cool because we just answered a lot of the stuff conceptually, right? And so I just wanted to pause right here to just point this out. So because our UE is equal to U final, right? And this is for scenario 3, we can make the huge jump, the huge conclusion that the kinetic energy initial is equal to the kinetic energy final at point 3. And so this is extremely helpful because the problem is looking for how fast is it moving. We basically solved it already conceptually because we know that the initial velocity and the final velocity has to be the same according to this ball chart or this bar chart. All right. So as we go from halfway, or let's see, is this even halfway? Is it 1 meter down? Did I do 1 meter down yet? I didn't do 1 meter down. All right. Well, we'll add 1 meter down in a little bit. All right. So here we have ball, earth, and now we're about to hit the floor. Nothing interacted with the ball at all. If you're wondering, Mr. Lee, we get it. Nothing's interacting with the ball. Well, just keep that in mind. Don't forget it. All right. So just so I don't want to record this video again. We didn't do part D, but we'll do part D. We'll do part D later. All right. So this is the energy bar chart model without part D. And so let's actually mathematically solve this. How high will the ball go? All right. So how high will the ball go is going from scenario 1 to scenario 2. So I'm going to identify that we're looking at scenario 1 into 2. All right. So we can say ME initial is equal to ME final at 2. So we can say, let's see, MGH initial plus 1/2 MV initial squared is equal to MGH final plus 1/2 MV final squared. All right. Now, I know some of you are like, I want to put in my zeros from the start. Don't do that, right? Write out this line. The reason why I want you to start off with this line and then go into this line is on the FRQs. Oftentimes you get a point for showing, hey, I know that I have to use the conservation of energy formula. All right, so you can get a point for having those two lines. It's really cool. Yeah, easy way to get points. All right, and we know that this formula is true because of what we set up here. right? Our initial energy and our final energy has to be equal to each other, and that's how we came up with this formula right there. All right, now let's apply some math. Well, before we do some math, let's solve this in variable form. We got to get into that habit. We're looking for the height, the max height, right? How high will the ball go? So we're looking for variable h. Now, for those of you with keen eyes, you can see that the masses here cancel out. Boop, 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 boop. And it's because there's a mass in each one of those formulas. And so we have G, oh my gosh, why is that so thick? All right, we got GHO plus 1/2 V initial squared is equal to GHF plus 1/2. Oh my gosh, where's my V? Where's my velocity? I lost it. Why is that so thick? There we go. All right, V final squared. All right. Yeah, let's identify our zeros at this point. We know that our velocity at the peak is 0. So 0 times anything gives us 0. All right, and so this cleans up our formula. So we get GHO plus 1/2 V initial squared is equal to GHF, and we're solving for this HF. And so we got to divide everything by G. GHO plus 1/2 V initial squared, all divided by G, gives us HF. Right. And if you want to be really good about your algebra, you can clean this even more. We can say G times HO divided by G. This gives us HO. 1/2 V initial squared divided by G gives us 1/2 V initial squared divided by G, like this. And at this moment, we can plug in our numbers. 2 plus 1/2, our initial velocity, what was it? 10. All right, so 10 squared gives us 100. 100 divided by 10 divided by half. That's 5. Yeah. All right, so that's 2 plus 5. And so our final height is 5 meters. All right, we did it. That's the answer for A. All right, speed run. Let's go from how fast will the ball be when it lands. All right, so at this point, we're going from our initial, so number 1, and we're going to number 4. Okay, so 1 into 4. Let's do this. 1 into 4. Well, we could actually go from 2 to 4, but there's no point in doing that, right? Because we have everything from our initial, and we know the initial start to be true. All right, so showing you good habits. Always start with the conservation of energy formula. We know that no energy is lost, so that is our formula. How do we know this, Mr. Lee? Because there was nothing interacting with the system, right? And so we know this to be true. We can say mg h initial plus 1/2 mv initial squared is equal to mg h final plus 1/2 mv final squared. All right, so that's our formula. Now let's get a little mathematical here. We know that at our final location, our potential energy here is 0, and so I'm just gonna cancel all this out. Right, get rid of all of that. We don't need that. All right. And we see that here, there's an m in every single one of these terms, so we can cancel out the masses. Boom, 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 boom. Yeah. And so our formula therefore becomes GHO plus 1/2 V initial squared is equal to 1/2 V final squared. All right. So we're looking for that final velocity. How fast is it going? Let's get some algebra up in here. I want to get rid of this 1/2, so I'm going to multiply everything by 2. So we get 2 GHO plus V initial squared is equal to V final squared. And our final answer, we just got to square root this son of a gun right there. And we get this. All right, and at this point, let's plug in our numbers because we're practicing good habits. For the FRQs. If it asks you to derive a formula using the given variables, this is what they want, but we want to be able to calculate it as well, because I know you all love that. All right, so we have 2 times G is just 10. Our initial position, what was it, 2? Our initial velocity, what was it, 10? So 10 squared, that's a hundo. All right, so 2 times 2 is 4. 4 times 10 is 40 plus 100. So this is a square root of 140. Oh my gosh. I can't do that math in my head. But that's the answer. Plug that into the calculator. Yeah, do it. All right. So this is the answer for, what is this? B. All right, we just solved B. Okay, so we just did A, we did B. How fast is it going when it reaches to a height of 2 meters? All right, so this one's important. This one's a very conceptual idea, right? I talked about it right here. We said, okay, so if our initial potential energy is equal to the final potential energy, that must mean our initial kinetic energy has to equal to our final kinetic energy. And let's see if that's true. So our prediction, right? So our prediction is that our velocity, if our velocity initial is 10 meters per second, our final velocity also has to be 10 meters per second with a huge, huge hold on there, okay? Because we know that as it's, when it goes up and it comes down, this is going to be 10 meters per second down. All right, start off with the formula. Let's see if this is true. Okay, we have UG plus KE is UG plus KE. And so for this one, we're going from scenario 1 straight into scenario 3. Okay, and if we check our graphs, we see that there's no zeros, right? There's no zero here, 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 or here. So we're left with doing this the long and arduous way. So we have MGHO plus 1 half MVO squared is equal to MGH final, which hint hint, wink wink, our H initial is equal to H final, 1 half MV final squared. So you know what, with this little hint hint, wink wink, I'm going to update this so that it matches what we just wrote, like so. All right. So let's get rid of things. Okay, so I'm going to subtract MGHO from both sides. So we get MGHO minus MGHO plus 1 half MVO squared is equal to 1 half MVF squared. Lo and behold, this little clause right here, it cancels out, right, because we're subtracting it. And here we have 1 half from both sides, so that cancels out. Oh my gosh, we have a mass on both sides, so those both masses cancel out. Oh my gosh, and so we have V initial squared is equal to V final squared. Square root everything. So we get V initial is equal to V final. Oh my gosh, we have a thicker pen here, but we don't care, right? And so, boom, this is our answer. But for those of you that paid attention in physics class, you'll write this as negative 10 meters per second. And that negative comes from it going down because our V initial is 10 meters per second up, and this V final will be negative 10 meters per second down. Oh, yeah. Good stuff. We proved it. We're proving physics left and right. Okay, and so just so you know, this is what we did in the kinematics unit. And if you're thinking to yourself, well, this is so much easier, and the answer is yes, it is easier. But the kinematics unit, we need to discuss the idea of time, so we weren't able to do this method. All right, so we did A, we did B, we did C. Now let's do the D. We didn't do D using the bar charts, and so we're not going to skip it. Right? We're not going to skip the bar charts. I know some of you are thinking, I want to skip the bar charts. Don't be that person. Okay, don't be that person. We're going to do the bar charts. Not only are we going to do the bar charts, but we're gonna sketch it as well. Don't be that person that doesn't sketch the problems. You don't want to be that person. Woo. It's a quick little sketch. It takes no time at all. All right. So here we have a height. We have a velocity going up. And here we have a height, and we have a velocity going down. Our velocity going up is 10 meters per second. Our height, was it 2? Yeah, our height was 2. Our height here is 1. All right, so potential energy, kinetic energy, total energy, potential energy, kinetic energy, total energy, system, ball, earth. Oh my gosh, my spelling, ball. All right, ball, earth. Nothing's interacting with the ball or the earth, not even air resistance. And so we can say our total energy is equal to our total energy. Final check. We gotta have those check marks. We gotta have these check marks in place. All right. So now let's solve it, right? Using the energy bar charts. So we know that we start off with some amount of potential energy, we start off with some amount of kinetic energy, and here we have some amount of total energy. All right. Here we can see that we're lower than our initial height. We're lower than our initial height. So I'm going to draw this a little bit smaller. Where did the energy go? Well, because our total energy doesn't change, right? So the remainder will be the kinetic energy. So what this shows you is that like this height plus this height gives you all of this energy, much like this height plus this height gives you all of that energy. Okay, so we can see that there's some amount of potential energy, but it's mostly kinetic energy. So it's moving faster. Yeah, it's moving faster. This is the big idea. It's moving faster. So in terms of a MCQ, this could be a conceptual question, right? It's moving faster or slower. It's moving faster. So let's prove it. Let's prove that it's moving faster. Initially, it was moving at 10 meters per second up. And so we want a number that is bigger than 10. I know that looks like a 16, but trust me, that's a 0. All right. Formula time. So we did all the conceptual stuff out of the way. Now let's do the mathematical stuff. Oh my gosh, the thick pen strikes again. All right, it's gonna change it. So this is struck again. All right, UG plus KE is equal to UG plus KE. These are all the final ones. Certainly you're getting lazy, I know. All right, so we got that. We have MGHO plus 1/2 MV initial squared is equal to MGH final plus 1/2 MV final squared. Okay, there's no zeros here, so we can't cancel anything out. But for those of you with a keen algebra guy, you can see that we have a mass here. Cancel, 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 cancel. Now, just so you know, you can only cancel it if there's a mass in every single thing. All right, so don't get like happy about canceling out numbers. We can only cancel out if it's everywhere. All right, so we're looking for our final velocity, so we're going to solve for VF. Once again, good habits, okay? This is what the FRQs ask for, so we got to start doing this. Notice here, I didn't cancel out the 1/2s, and that's because not everything has a 1/2, so I'm not going to cancel it. All right, so if you wonder what I just did, I moved that over there by subtracting it from both sides. And now I want to get rid of this 1/2 by multiplying everything by 2. So we get 2GHO plus V initial squared minus 2GHF. All right, VF squared. I don't skip steps. I don't skip steps. You don't skip steps, right? That's the rules. And the very last thing, we're going to square root everything. So our final velocity is equal to square root of 2GHO plus V initial squared minus 2GHF. Yeah. Now, I don't know if you see this, but this right here is actually, this is a kinematics formula. Oh my gosh. This is really cool. So, quick little tangent. I don't want to let this opportunity go. I'm just beside myself here. I'm having the time of my life. So, if we, let's see, let me just do this. Oh my gosh, this is so cool. Okay. Oh, wow, look at this. Yeah, this is nifty. All right, so I just moved the VO over. We get this, and if I take the 2 G's out from everything, we get HO minus HF equals this. Yeah, that's actually the kinematics formula. Would you look at that? The kinematics formula, I believe, is VF squared is equal to V initial squared plus 2G delta X. So here's the 2. Let's highlight it. There's a 2. There's a G. There's a change in height. All right, here's a VF. And I just moved this VO over. Would you look at that? There's a kinematics formula. That's really cool. So we can see where the kinematics come from. That's important. Why? Because remember how I said this is just like the kinematics unit with one huge exception. There's no time in this. And notice here, this formula here, there's no time. There's no time, suckers. And so because there's no time in this formula, it looks exactly like our kinematics equation. It's really cool. I appreciate it. I don't know about you, but that was really cool. All right, so 2G is 20. Our initial height was, what was it, 2? So 2 times 10 times 2. Okay, showing you good habits. Don't skip these steps. HF is 1. Okay, show all your work so that others can help you out in case you get a wrong answer. If you skip your steps, no one can help you out. 2 times 2 is 4. 4 times 10 is 40. Plus 100 minus 20. Oh my gosh. All right. What is this? Root of 120? What does that give you? More than 11. more than 11, less than 12. So VF is roughly 11 meters per second, right? Because 11 is 121 and this is 120. So it's roughly 11 meters per second. Whoa, look at that. We said it was going to be faster, and it is. 11 is bigger than 10. We're physicsing. Yeah, it's more than just algebra. It's math. It's logic. Anyways, those are 4 example problems. I'll see you later. Bye.